Hi, I'm Emily Herbert, and this summer I worked for Professor Victor Lee in the Advanced Civil Engineering Materials Research Laboratory. My research was focused on the monitoring of self-healing in engineered cementitious composites using electrical impedance spectroscopy. Engineered cementitious composites, or ECC, are more commonly known as bendable concrete. They are an ultra-ductile, fiber-reinforced cementitious material with a tensile ductility that ranges from 3 to 5%. The top picture shows just how ductile this material can be. Microcracks form during loading, and ECC is engineered so that these microcracks are, on average, less than 60 microns in width. These small crack widths enhance ECC's ability to undergo self-healing. Healing occurs when a damaged sample is exposed to water and the cracks begin to fill with what we believe is calcium carbonate. The bottom picture shows 4 cracks before and after self-healing, and as you can see, the cracks become completely filled with self-healing products. As we all know, concrete structures, such as bridges, can be damaged during their service life and become hazardous to the people who are using them. Current methods used to detect structural damage are not adequate. Some methods, such as visual inspection, can only see the flaws on the external portion of the structure and may completely overlook internal damage. For this reason, we are exploring the use of electrical detection methods. Electrical methods could lead to wireless monitoring of structures and real-time damage detection, which could greatly enhance the safety of any structure that uses these methods. ECC can be used with these electrical methods because it is a piezoresistive material. Piezoresistive means that the electrical resistance of the material changes with strain. This occurs because the material cracks when it's subjected to tensile strain, which means that there are gaps formed in the matrix, and these gaps increase the resistance. For this reason, when self-healing occurs and fills the cracks with healing products, the resistance should decrease because the gaps in the cementitious matrix are being filled. For my experiment, I will be using electrical impedance spectroscopy, or EIS, to measure the impedance of ECC before loading, and after self-healing. Like resistance, the impedance of the material should increase as damage is induced and decrease as self-healing occurs. For the test that I'll be doing, I'll start by mixing a batch of M45 ECC and casting it into coupon samples. This picture shows the coupon sample after it has been demolded and prepped for tensile loading. I'll use 3 coupons as undamaged controls, and since EIS can be sensitive and works better with fairly small sections, I'll be cutting each coupon into 2 smaller sections to give a total of 6 control samples. I'll also have 6 damaged samples. However, unlike the controls, before cutting the coupons into smaller sections, I'll preload the coupons to 0.3% tensile strain, which will create cracks in the samples. In order to do EIS, 4 electrodes will have to be placed on each ECC sample as shown in this small diagram. The electrodes consist of copper tape and silver colloid paste. The conductive silver paste will act as a glue to adhere the copper strips to the sample and ensure proper contact between the ECC surface and copper tape. The 2 outer electrodes will apply a current to the sample, and the 2 inner electrodes will take the measurements. After the electrodes have been properly placed, EIS will be used to measure the impedance of the 6 undamaged controls and the 6 preloaded samples. After this first EIS measurement is taken, all 12 samples will begin to undergo wet-dry cycles. Each cycle consists of 24 hours submerged in water and 24 hours in air. This cycling will ensure that self-healing occurs and EIS measurements will be taken on each sample after every wet-dry cycle. Instead of giving a single impedance arc, EIS gives an impedance arc with both real and imaginary parts. Because of cracks in the damaged samples, I expect that the first damaged impedance arc will be much larger than the control sample arc. After each wet-dry cycle, the cracks in the damaged samples will be filled with more and more healing products, thus decreasing impedance. For this reason, I believe that the arcs for the damaged samples will get smaller after each wet-dry cycle and will possibly shrink back down to the control sample arc after enough cycles have occurred to allow for complete self-healing. In conclusion, the basis of my research is to explore the use of the electrical testing method, EIS, to monitor how ECC properties change as damage and self-healing occur. This is being done because current structural damage detection methods are not adequate and the safety of structures could be greatly improved by using electrical methods to monitor damage and any self-healing that may occur. If you'd like to know more about ECC and the research our group does, feel free to visit our website at acemrl.engine.umich.edu. Thank you for watching.